Alright, so why do casinos always win? Why are they guaranteed to win? And win lots with very little risk. Recall that in roulette, if a gambler bets $1 on red, they have an 18 out of 38 chance to win $1 and a 20 out of 38 chance to lose $1. Here is the probability distribution for the variable x, which is the casino's winning. So I'm flipping the winnings here. Instead of talking about how much the gambler wins, I'm going to talk about how much the casino wins. So the casino is going to win $1 20 out of 38 times and lose $1 18 out of 38. So they got a better chance of winning. If you remember, the mean and standard deviation was about 5 cents, and the standard deviation was about $1. So what this means is the casino is going to win on average 5 cents per hand, per roulette roll, if the bet's $1. And the standard deviation is going to be 1 on average, and that should make sense that this is 1. Either they're going to win $1 or lose $1, so it should be on average pretty close to 1 for distance from the mean. Find the mean and standard deviation of the casino's winning after 2 games. So suppose the casino wants to look at their winnings after 2 games. So I'm going to play the game twice, x1 and x2, and I'm going to add up the winnings from both games. So the expected value for the winnings of 2 games is going to be the expected value of the winning for the first game plus the expected value for the winning at the second game. These are obviously the same. They're both the 0.0526, which is basically just 2 times 0.0526, which is about, what, 10 cents? 10.32? What, it doesn't really matter. Whatever. About 10 cents. How about the standard deviation? Well, first of all, can we calculate the standard deviation? Is the first game of casino independent of the second game, or the second game independent of the first game? And they are independent. What happens on the first game doesn't influence what happens on the other game. So we can add, but remember, we don't add the standard deviations, we add the variances. So the standard deviation is going to be the square root of the variances added together. That's 0.9986 squared plus 0.9986 squared. That is 2 times 0.9986 squared. And then take the square root of it. Square root 2 times 0.9986. Left them at 2 squared. 1.41. So if they play 2 games, and this is kind of the key idea here, is if they play 2 games, they double their winnings, but the standard deviation, which is kind of a measure of their risk, I mean, if they're going to win 5 cents, but the standard deviation is really high, it's entirely possible that they're going to lose a lot of money or win a lot of money. So when you play 2 games, their expected value doubles, but notice their standard deviation doesn't double. Their risk isn't, I mean, it's still a lot of risk. If you're 10 cents and the standard deviation is $1.40, this is still not a good bet for the casino. All right, but what if we play 3 games? The expected winnings after 3 games is going to be the 0.0526 plus 0.0526 plus 0.0526, which is simply 3 times 0.0526, which is about 15 cents. I'm not going to worry too much about the decimals. Standard deviation, square root of, add the variances. The variance is 0.9986 squared, and I got to add 3 of the variances because there's 3 trials. Which is 3 times that. 1.7. So we're still not a very good bet. But if we keep kicking this up, what if they play 10 games? Well, 10 games, your expected winnings are going to be 10 times 0.0526, which is now, we're talking some big money now. That's 53 cents. And the standard deviation is going to be square root of 10 times the variance. Is this a good bet yet? Probably still not a good bet yet. $3.15. Still not a good bet for them. But here's a table of this projected to many, many games. 100 games, they can expect to win $5 with a standard deviation of 10. So they still got a chance of losing. You know, a couple standard deviations below the mean and they're losing. 1,000 games, getting closer. This is a better bet now. They're probably going to make about $53 and their standard deviation's $31. So there's a good chance they're going to win money on that one. We get up to 10,000 trials and now they're practically guaranteed to make their money. Whoa, I didn't know that did that. They're going to win $500 on average and a standard deviation of 10. So even if they have a very, very bad day and they lose like 3 standard deviations below the mean, they're still going to make their money. Kick that up to 100 million times, which is a little ridiculous, but that's $5 million. And look what happens to the standard deviation. Look what happens to the casino's risk. Plus or minus, $10,000 or $20,000. This is a great bet. This is a good investment. Now you might say 100 million times, that's pretty unrealistic, but this is just a bet of $1. Casinos don't even let you bet $1. Minimum bets are sometimes $3 or $5. And people are betting a lot more money. So they don't have to run 100 million games to make their money. They're going to make their money in here. This is the same idea with insurance companies. They give an insurance policy. If somebody gets hurt or somebody dies in an insurance policy, the company's got to pay a lot of money, but they don't have to pay it that often. And if they have a lot of policies, they're going to make their money, and it's actually fairly predictable. Not a lot of risk. Okay. All right, let's just keep going. Suppose a certain variety of apples have weights that follow a normal distribution with the mean. So let x equal the weight of one apple. So the mean is 9 and the standard deviation is 1.5. If a bag of apples were filled by randomly selecting 12 apples, what is the probability that the sum of the weights is less than 100 ounces? So we're going to calculate a total weight. Now in class we kind of talked about, is that 12x? Or is it x1 plus x2 plus x3 plus ... plus x12? Which one is the case here? What does this one mean? This one means you take one apple and you multiply its weight by 12. This one means you take 12 apples independently or separately. And again, these questions should say assume independence. We need to assume that the weight of one apple is independent of the weight of another apple. This question really should say it. On the other ones I wanted to talk about it, but this one should have said it. This is taking 12 different apples and weighing them together. That's two different things. You're going to have different amounts of variability depending on which ones we do. In this case, we're doing this. So the expected value of t is the expected value of x1 plus the expected value of x2 plus, but since these are all the exact same random phenomenon, just different trials of it, it's going to be 12 of those 9s. Is that 108 ounces? Standard deviation of t. Again, the real common mistake is just to take 12 times the standard deviation. Nope, that's what you would have done here. That's not what this is. This is take the square root of, add the variances. 1.5 squared plus 1.5 squared plus 12 times. That is 12 times 1.5 squared. Square root 12 times 12. You stupid thing. Jeez. Square root of 12 times 1.5 squared. 5.196. 5.196 ounces. Now, if a single x1 random variable is normally distributed and we're adding 12 independent ones, then t is approximately normally distributed as well. So I want to find the probability that my sum is less than 100 ounces. My total weight is less than 100. Mean is 108. Standard deviation is 5.196. Less than 100, 5 is going to be, one standard deviation is going to be about 103, somewhere right around there. Be pretty small. Normal CDF. Lower bound negative infinity. Upper bound 100. Mean 108. Standard deviation, oh geez, 5.196. I can't remember. 5.196. Boom. 6.2%. 0.062. Okay. What if, ooh, we're at 11 minutes, next video.